Does that work?
That worked.
Okay. I think your audio is the wrong device.
Oh, really?
Tap your microphone.
Okay.
And you've spelled CosmoQuest right this time.
We all make mistakes.
That sounds way better. It was ComzoQuest last time.
Oh dear.
I forgot to mention he's the director of CosmoQuest. I'm gonna write that in my intro. Hi everybody.
Welcome to us preparing to start the audio recording of the show and inviting you in to watch backstage how everything gets done.
Yeah, exactly. Right, so hi everyone. My name's Fraser. I'm the publisher of Universe Today, and there's Dr. Pamela Gay, my co-host on Astronomy Cast, and this is an impromptu catch-up episode of Astronomy Cast. So as you may know, we're a few episodes behind, just a couple, not many, and so we are absolutely committed to catching these up as quickly as humanly possible. And so we're going to be doing a few more of these impromptu episodes and catching them up to the feed, because I know the feed is a little behind as well. So, so thank you everybody who has noticed this is a problem. It is a daily reminder that we are behind, and we will get caught up. So today we're going to do a live episode of Astronomy Cast. We're going to record that. It'll take us about half an hour, and today's episode we're going to be talking about the observable and unobservable universe. And so that'll take us about half an hour, and feel free to make any comment, questions, posts while we're doing the show. Sylvan Westby wants to remind you, are you recording in stereo?
No, I'm not. Valid question.
Valid question, very valid. And so you can, by all means, make any comments or questions in the various places, and I will be watching them. And if we make a mistake or if you catch something we need to fix, I will try to incorporate that into the show. So there's a bunch of places you can do that. You can make a comment or question on the event page on Google+, or if you're watching this on my feed or on Pamela's feed or somewhere on Google+, you can make a comment there, and we'll try to get all of those sources. I make no guarantees. It's a little tough to catch them all. And then probably the safest place, if you feel like no one's noticing your comments, is to make a comment over on YouTube. And so you can access the YouTube video. Just wherever you see the YouTube video, click on it and then watch it on YouTube, and you'll see separate comments that are running along YouTube, and you can post your comments in there, and we'll definitely get those. So that's sort of like the safest place. And then also, if you're watching this somewhere else and you like to use Twitter, we can catch that. Just use the hashtag Astronomy Cast. And so during the show, just keep the chatter up, and we'll sort of incorporate any of those comments. And then after the show, by all means, make any comments or questions, and we'll try to stick around for a few minutes and answer your questions. I'm not sure how much time you have today, Pamela.
I have a date with my horse at 5 p.m.
Okay, well, you're in the future. 3, so 4. So we kind of want to get out of here for you around like 4. So I'm not sure how long it takes for you to get to the horse, but
I usually I leave my house to go meet my horse at 5. So we have about an hour and a half, 2 hours.
Yeah, but we're not going to stick around for an hour and a half, 2 hours. We'll probably stick around for 15, 20 minutes after we do the show. So
I just wanted to see you convert time zones in your head.
That was an easy one because you're only 2 hours ahead of me, so that was not so bad. It's when we have to convert 3 or 4 of them all at the same time is when it gets complicated. Okay, cool. Well, let's get rolling then. I'm ready to press record. If you're ready to press record.
Yeah. Pressed record.
Testing. Yeah, that's good.
I am recording.
All right, let's do it. Here we go. Astronomy Cast, episode 295 for Monday, February 25th, 2013, The Observable Universe. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. Do we have any announcements or things to talk about?
We do. We
Okay.
are continuing to advertise for the classes that are going to be starting soon through CosmoQuest. You can get to them by going to CosmoQuest/classes.
CosmoQuest.org/classes?
Yeah, cosmoquest.org/classes. And we currently have 2 upcoming classes. One of them is on the sun, stars, and stellar evolution. That one is taught by Rain Sanders, who goes by Dear Astronomer on Twitter. The other class is cosmology, taught by Dr. M.R. Francis Matthew. He shows up as Dr. Mr. Francis on Twitter,
Mr.
which
Francis.
amuses me to no end.
Yeah.
He is teaching a class on cosmology. Both of these classes are starting shortly in April, so you can go to cosmoquest.org/classes, check out the dates, check out the times, and hopefully you'll sign up through Eventbrite. Nicole Gallucci and I will both be making random appearances in these classes and contributing where we can. And this is one of those ways that we help employ people who are in astronomy, so we do ask you to please pay. This is part of how these 2 individuals make their living. Sorry that we can't do everything for free. I know we would if we could. But we're hoping that you'll sign up. Each is 8 hours long and jam-packed with information. And the classes are limited to 8 people each.
Perfect. All right, let's get on with the actual show part here. So we understand that our place in the universe, because of the direct observations, we can see the light that travel billions of light years across space to reach us. This sphere of space is the observable universe, everything we can detect. But it's really just a fraction of the larger unobservable universe, and today we'll talk about both. So when we sort of talk about the observable universe, and I know it's sort of like the name is what it is. What
and we
is
often
it?
say the universe because we're lazy.
Right, but the universe is not right, and we need to make that distinction, right?
Yes.
Because the universe is the observable and unobservable theoretical universe. So okay, so let's start then with the universe, and then we can further sort of define our terms here. So what is the universe?
The universe is the entirety of the space-time continuum which we occupy, that is some sort of unknown geometry that many of us, myself included, think is a unbound finite size. Which is sort of how you define the surface of a sphere. So you can start anywhere you want on the surface of a sphere, and as long as you stay on that surface, you're never going to hit an edge. But that's currently what we believe it is. The universe.
Now, and I think we all imagine it as this sphere. Right?
And a more accurate way of looking at it, because we know parallel lines stay parallel to one another, is actually a donut. So you can start anywhere you want on the surface of a donut, and you never hit a boundary there either. But the thing is,
so the universe is a donut?
The universe
acts like a donut, right?
Yeah, it's technically more like a 4-dimensional hypertoroid, but donut works.
Okay, wait a second. So we went from is the universe a circle? No, the universe is a sphere. No, the universe is a donut. No, actually, the universe is 4-dimensional hypertoroid. This is not helping.
Well, okay, so we're just going to stick with Homer's donut for the rest of this episode and just realize the actual universe uses more syllables and it has a higher Scrabble value.
Right, but the issue being higher Scrabble value. The issue being that we're a little silly today. The issue being that with a torus, you get parallel lines moving in any direction. That you can move around the ring of the donut, and your lines stay parallel. You can move around the doughy goodness of the donut, and your rings stay parallel in both directions, and so the universe acts
this
like
isn't actually a donut, but we can pretend because it has the side of a donut. So you can imagine as things race around, the 2 lines stay parallel to one another. As they race around the top, they stay parallel to one another. And if this were a donut with a better hole in the center, you could have lines going through the center.
Right, which leads to the question of, like, where's the hole?
Well, that's the thing, is if you're confined to the surface, you can't figure that out. And we're trapped on the 4-dimensional version of this donut.
Okay. All right. So imagine a donut with a bunch of galaxies inside of it.
On the surface of it.
But only on the surface of it, not in the inside of it, and there's no hole. That's the whole universe. And I mean, as we did in the episode of, like, what is the universe expanding into, the universe is everything that there is. And so if you wonder what's outside the universe, well, if that's a thing, that's part of the universe. And so that's also in the universe. And so there is no...
Science can't get there from here.
Right. And anything that you can sort of include that you might think, well, maybe the universe is expanding into that, well, that thing is also part of the universe. So
if you want to discuss what's outside the realm of the universe, you have three directions you can go: philosophy, religion, or multiverses. Pick one.
Yeah.
None of them have scientific evidence at the moment.
Right. And the fact that, if it is, then it's part of the universe. I mean, that's the great thing about the universe is everything, and that way, if it's something, it's part of everything.
Well, okay, so this is where the space-time continuum part comes in.
Yes,
so
the timey-wimey...
Yeah, our universe has its own specific timey-wiminess.
Yeah.
So it has its own cosmological constant. It has its own value for the Hypervine structure. It has its own value for the gravitational constant. And if our universe is one of a multitude of multiverses, some of those other universes that are outside of our universe, according to this not scientifically testable concept, they could each have their own timey-wiminess.
Right.
They could each have their own
Don't forget
value.
the wibbly-wobbly.
Their own wibbly-wobbly.
Yeah,
they could
timey-wimey, yeah.
Right.
And as we understand it, this universe came into existence with the Big Bang and has been expanding for 13.8 billion years, and now is of a certain size.
Yes.
Okay. So that is the universe, and so then as a subset of that universe is the observable universe. So what is that?
The observable universe is everything that we can see until we hit what's called the wall of first scattering. This is the cosmic microwave background. And there is universe beyond that, but we can't see it because of this opaque wall of microwave background radiation.
Is that also a donut?
So
it's a sphere, right?
Now, here's where it gets confusing, because we're attached to the surface of this four-dimensional hyperdonut thing.
Mm-hmm.
And our observable universe is a sphere within that surface, because it's four-dimensional.
A four-dimensional sphere wrapped to the surface of a
three-dimensional sphere wrapped to the surface of a four-dimensional object. Okay. I didn't say I wasn't going to hurt you with
No. I love that I even was able to get partway there. I feel really proud of myself that I was able to think of it as a three-dimensional sphere. I just went one dimension too high, but no, we're okay. Right. Okay. So you got a three-dimensional sphere wrapped to this four, but it being but as we understand it, we look in all directions out from the Earth and see in 13.8 billion light years in every direction.
Minus 400,000.
Planck's new number, 13.8.
Right, no. Minus the 400,000 for when the cosmic background formed.
For the scattering, right? Okay,
yes.
So we've got the out to that age, and so can you explain sort of what is that first scattering?
So what happened was our universe formed. Everything was compacted down to a small point, and then that small point, all of it expanded into this donut. Now there's no center to this. The entire donut, so like suck all the air out of a donut to a microscopic point and then blow air into the donut. There's no center to the surface of that donut at any point in time. Never a center.
Right.
And
the center of the donut, the center of the surface of the
surface of the donut.
Yeah.
And at no point was there a center to that surface. Now, initially, everything was so compacted that it was pure energy. And as it expanded out, that expansion caused it to cool, caused it to lose density. Eventually, we were able to have protons, electrons, neutrons start to form, not necessarily in that order. And as these things formed, they stayed in this constant scattering with the photons, and everything was constantly interacting. And because of this constant interaction, we say that it was all in equilibrium together. Another way to think of it is a photon, as it went, couldn't go far enough to actually escape. It was just constantly getting absorbed and re-emitted in all directions, so it was also opaque. And then at a given special moment, everything reached a low enough density that a photon, as it tried to travel, didn't necessarily get reabsorbed. And that meant that it was able to fly free. And that moment when the photons were able to fly free from the point where I am, from the point where you are, and from the point we observe 13.8 minus 400,000 years ago, we're able to see that shell of objects, photons, that were released at that moment when the universe suddenly was big enough that they could fly free without getting reabsorbed. And that's just a shell of, at that time, that corresponds to that distance, because light travels at a finite speed, all those photons have finally just now had time to reach us. So we see them.
And I think that's just, again, mind-bending. The fact that in every direction you look, you are seeing, was it 400,000 years after the beginning of the universe? And that's the wall. And so wherever you look out in space, yes, you are looking at essentially the beginning of the universe. You just,
And what's cool is no matter where you go in our universe, when you look out, you will see a different sphere, but it's always coming from that same time, and it's always the same size sphere around you. So it's just, it's nothing more than a light travel time distance. It's actually, while the physics is different, conceptually it's very similar, and I've used this analogy before, to having a globe of light underwater, and you can only see this one sphere around you if you're in very deep, lightless water. And as you swim around, you carry your sphere of illumination with you.
And if you were to move, like if you see like just a fish over there and you're to move over to that fish, you might be centered with that fish, but now you'll still be seeing this sphere of water illuminated around you. Yeah, it's an amazing idea. And so, but it gets weirder, right? Because if I was able to travel out to the edge of of the observable universe to me instantly, I would now be there, but it would now be present day for that position, and then I would be seeing the universe again here as the beginning of the universe. So it's that extra like time machine part.
It makes you wish you could be Q or Doctor Who.
Yeah, and it's that part that it's both you're looking out and you're looking back in time at the same time that makes it a little extra bit of a head scratch. But also, and I think this is sort of part of why we're talking about this show, is it gives us this insight into the universe. Without that time machine aspect of this observation, we wouldn't know anything about really the true nature of the universe, because we'd be seeing everything now.
And one of the things that really bothers a lot of scientists is we live in a somewhat unique time when the universe has been expanding long enough that life can exist. That's useful. But it hasn't been expanding for so long that the distant observable parts of the universe have been carried back away from us so that we can no longer see them again. We can see the cosmic microwave background. We can see the first galaxies that formed. We can see even the first stars that were forming. Yeah. In the future, that's not going to be true, and that's kind of annoying.
Yeah. So then, and this is, again, if we are looking in this direction, we're looking 13.8 billion light years. We're looking that way, 13.8 billion light years. How big is the observable universe?
And this is where it becomes well, tell me exactly how you want to think about this question. Do you want to think about where were those things when the light was first given off? Do you want to know where those things are now? So the crazy thing about how this works is when we look at light from the most distant objects, that light has only traveled about 7 billion light years. But those objects are currently 47 billion light years away. So light...
Sorry. Man, okay. So those objects, light has only been traveling for 7 billion light years. So the light is only, is the light 7 billion years old? Because we're seeing it as it was emitted 13.8 billion years ago.
That's the distance the light traveled?
Because the universe has expanded since then.
Yes.
Right. And so the light was given off, and the light made its way in our direction.
Yes.
But then the universe expanded. To use our analogy, we always talk about these sidewalks that are increasing in number of squares. And so by the time the light finally makes it to us, it's had to travel an additional 7-ish billion light years of distance beyond just it moving at its regular light speed because of this expansion of the universe, right?
Yeah.
Okay, so we've got that sort of. Actually, the light's only been traveling for 7 billion light years from 7 billion years from its perspective. Actually, it's only traveled 13.8 total billion light years in space. But then you said 47
light years away
is where
now.
it is right now.
Yes.
So, like, the universe is like the observable universe is really about like 92, 93 billion light years across.
Yes.
Where those things are now.
So 47 is 94. I'll go with that one.
Okay, 94. Yeah. That's big. That's big. And yet, and I think this is really important, what percentage is the observable universe compared to the unobservable universe?
So based on the notion that our universe is a bound surface, and so that means that the light can start, and as it travels, it will, given the fullness of time, hit you in the back of the head. So this is the Pamela shines a laser beam, light comes back, hits the place where my head would be had I not died and crumbled to dust.
Right.
But we've tried to look for places on the sky where we can see these patches of light that were both emitted from the same place, where the patch of light expanded in 2 different directions. And we can't find those. And so based on our current understanding of physics, this limits us to being only a few % at most of the entire universe.
By volume?
By volume.
Right. So, and now the math is getting away from me here, but like if it's a couple of % by volume, volume pi 1/3.
Don't go there. It's a lot. It's a big number.
It's a big number. Like several hundred billion light years across? A thousand?
So it
trillion
would be
light years across?
Well, so if you're only doing a few % and you're looking at the diameter, then if a few % is 94 billion, then we're looking at trillions and tens of trillions of
light years, yeah.
Yeah, minimum.
Right.
Minimum is tens of trillions.
Tens of trillions. And if it were any smaller than that, then we would see these situations where in the early universe we saw light going in both directions and getting this kind of this mirroring. And we don't see that.
We don't see that. Planck was our next best hope, and we still haven't found it in the Planck data.
And, for those who don't understand, can you give sort of people sort of an overview of what Planck was and sort of what this, because there's a big finding that just came out, by the time we're talking about this.
Right. So the Planck mission has taken the newest, most highest resolution, most sensitive measurements of this cosmic microwave background that we keep returning to. And we have an entire episode from our first year dedicated to this wall of light. And it was initially observed from the surface of the Earth, but microwaves don't get through our atmosphere so well, so we couldn't really see anything in high resolution. Attempts through high atmospheric balloons were made. But finally, we were able to use the COBE satellite. That allowed us to see that there's only a few % difference point to point in temperature variation across this wall of light. We then used the WMAP satellite, the Wilkinson Microwave Anisotropy Probe. It did the next highest resolution one, and it allowed us to finally start figuring out that the space we live in has Euclidean geometry, which I like because that math is easier. And then with Planck, we're looking at things in even higher resolution, trying to better understand the expansion rate of the universe, trying to better understand the acceleration of the expansion rate of the universe, and trying to understand what is the density parameters of our universe. And with the recent release of the Planck data, we realized that the age we had for the universe that had error bars on it, the modified age fits within the error bars of the old age, but it's been refined to be 1,000,000 years older than we thought it was, which is kind of cool. And
right, so the universe is older, but also, you know, and I know we did in a weekly space hangout, we were talking a bit about how it has some implications for inflation. And there's some things that people were wondering about. There's like a cold spot that's kind of a mystery. So, you know, very interesting findings that came out of Planck.
Second show maybe to come.
Yeah, that might be great. Have we done it? We done a Planck episode?
I don't remember. We've done 295,
yeah,
and my audio stopped recording.
What? When?
It stopped at 14:02.
Oh no! Audacity.
No, this was actually, I had an Apple system update, so everything froze except for this Hangout.
Okay, let me see. I'll stop mine.
Let me listen to what my last thing was. Sorry, folks.
Oh, this makes me sad.
And this... Okay, so that's apparently the last thing I said. Let me see what I said before that. And try and turn down the volume. Forming. In the future, that's not going to be true, and that's kind of annoying. Okay, so that's the last thing I have, and then you said something.
I say a lot of stuff.
Yeah, I have a feeling.
Okay, what's your time code?
It died at time code 1402.
1402.
I think it died right when I said that in the future we aren't going to be able to see. Sorry, Preston, you're not actually going to hear this because I'm not recording. I will have to apologize to you in a moment.
Okay, so you're not going to be able to hear this.
Forming. In the future, that's not going to. In the future. Sorry, I'm trying to figure out exactly what this is.
And what was your time code?
We no longer see them. 1402. We can see the cosmic microwave background. We can see the first. Okay, so I have whatever you said after I talked about. In the future, we won't be able to see the entirety of the universe. In the future, we won't be able to see the cosmic microwave background.
So then I asked you, how big is the observable universe?
Okay, so I guess we're going back to how big is the observable universe.
Yeah, and so the I'll pop my speakers out here for a second.
Okay, sorry everyone.
They love it.
Okay, I'm going to insert a apology to Preston into my audio.
7 apologies per second. Here. Okay.
Hi, Preston. Sorry to do this to you, especially while you're working on your thesis. My audio died rather suddenly, and so there may be a bit of chaos that is about to occur in our audio. So sorry.
So I'll start recording. I'm going to re-ask this. Oh, here's the question, and then you can... Okay, so can you hear this? Yeah. So then, and this is, again, you know, if we are looking in this direction, we're looking 13.8 billion light years. We're looking that way, 13.8 billion light years. How big is the observable universe?
Okay.
And that's where we went into, it's 7 billion, it's 14 billion, it's blah, 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 right?
Okay. I can pick that up.
And so I will cut my audio there, and then we will, if that's going to work here. Let me just make sure I did this right, and I will just delete it, and then I will start a new track right at that point. Oh. Yeah, okay. All right. How big is the observable universe? And then we'll talk about that, and then we'll talk about how big is the unobservable universe and sort of that scale, and then we'll talk about Planck again. So, okay. I'm going to just put my headphones back in.
Tell me when to press.
Okay. So a bunch of people wondered about whether we can use YouTube for this. We can, but the audio quality on YouTube is crap.
Sucks.
Yeah, and so it just sounds horrible compared to our sort of better setup. So that's okay. We do this. This has happened before. This is not the first time.
Yeah, you could just get to see it now that we use the Hangouts.
Now that we do the Hangouts, yeah. All right, are you ready?
Yeah, I'm pressing record again.
I'm also pressing record.
Okay, sorry, Preston.
Yeah. Okay, so
very
then
good.
I just asked you, how big is the observable universe?
Well, that all kind of depends on what you're asking. And this is where it gets really confusing, because it turns out that light that we're seeing from the most observable objects, not the most observable, the most distant objects, that light has traveled from an object that was 7 billion light years away, but it's now 47 if we were able to see it right now. Right now it's 47 billion light years away.
Okay, so hold on a second. Let me see if I get this straight here. So that object, when it emitted the light that has gone from it has traveled for 7 billion years from the light's perspective. Although,
Yes.
you know, the photons are timeless and they don't really understand time.
Yeah, they
right.
have no time. But the
from-
universe has
right, if we could
expanded during the
watch-
journey.
Right, so if we could watch that photon moving along, it would have moved for 7 billion years from its perspective. But yet, the universe has been expanding, and so it will have traveled a total distance of the 14.8.
47 billion.
Well, no, but it's traveled for I guess, for 13.8 billion light years from our perspective. But actually, if you could sort of look at its current location now, it has moved a total of 47 billion light years. So I'm going to do some sort of quick math here then.
So it's moved from an object that was 7 billion light years away
Yeah.
to us over 13.8 billion light years,
Or
and
billion-
that
yeah,
object
billion
is now
years.
47 billion light years away.
Right. So then the size of the observable universe is 94 billion light years across.
Yes. So here we are. Light from the right has come from objects that are now, we can't see them now, but they are now 47 billion light years away. To the right, to the left, add those two numbers together, we end up with the diameter of where things are now of 94 billion light years. And the light we see was released when it was much closer.
Right. Okay. But that's the observable universe.
Yes.
So then the question is, how big is the unobservable universe?
And we don't know. So this is one of those awful things of the one thing we do know is we've searched the sky for those moments where the light that's released going in two different directions, it goes forward, it goes back, and in theory you should see the exact same thing if the universe is small enough, coming at you from two sides. This is the idea of I shine a laser beam out my face, and as it zips around this donut-shaped universe, given the fullness of time, it will come back and hit where my head was, except I'll kind of be dead and dust by then. Now, the thing is, when we look for these places where the light has been emitted in all directions, and we should see the beam going forward and going back, coming together at two different parts of the sky, we don't see that. And that means, from our best understanding of modern physics, our universe is so much larger than what we can see, that what we can see is probably only a few % of the greatness of the actual universe.
Right, and we've talked about this in previous shows, that the universe could be infinite, or it could be finite, but it's just so big that we're not seeing this curvature, we're not seeing this mirroring of the light in our observations. And I know that scientists working with the Planck mission recently released the most accurate map of the cosmic microwave background radiation ever done, much more sensitive than was done by WMAP before. And so, that must have pushed things back even further. So, if people maybe haven't heard about this, so what happened with the Planck mission?
Well, the Planck mission is our newest, most sensitive, most high resolution mission for observing this wall of microwave background radiation. And prior to it, we'd initially discovered the cosmic microwave from the ground, but the light doesn't get through our atmosphere so well, so we couldn't really understand it very well. There were balloon-based missions to try and look at it from high enough up in the atmosphere. Eventually, the COBE satellite did an all-sky study. This was followed up by the Wilkinson Microwave Anisotropy Probe, WMAP, which allowed us to figure out that the geometry of space is flat, allowed us to get our initial measurement that our universe is 13.7 plus or minus zero point 0.2 billion years old. And then along comes the newest mission, the European Space Agency's Planck, and it continued to look at the sky, continued to help us try and better understand what is the expansion rate over time, how fast are we accelerating in our expansion, what was the mass density of our universe. And part of that was also looking for these places where you see the two different points on the sky reflecting the same point in space where light was released. And we haven't seen that, but we do have a better age of the universe. It turns out that the age is determined using Planck data is within the error bars of the old measurement, but it's now 1 million years older than it used to be. So the universe was apparently hiding its age.
Right. I think before we would always say 13.7, and now we get to say 13.8. So that's the new number we're using, 13.8 billion light years old. But right, and so you can then imagine, right, you know, that if the observable universe is this 94 billion light years, but it's only a couple of % of the entire universe itself, based on this Planck data. You know, the math is now failing me, but we're looking at a universe that is hundreds of billions, trillions of light years across?
Not trillions is still too small of a number. So if a few % is 94 billion, then you're looking at tens and tens of trillions, maybe even hundreds of trillions of light years in this four-dimensional crazy space across. And so these start to become numbers that we can't even really, as humans, begin to understand.
That always makes me sad, you know, because there's like all this universe that not only will we not discover and see, but there is no possible way that it is outside of the laws of physics that we can never reach this stuff.
Well, things are going to get worse. One of the things that frustrates me is things that are 8 billion light years away are already moving away from us at the speed of light. At some point, the amount of light that we're able to see from other objects is going to get to the point, because everything's running away at such a high velocity, that we're pretty much only going to be able to see the galactic supercluster that we eventually fall into. So it could be worse. We're actually pretty lucky to be able to see all the large-scale structure that we're able to see today.
Right, and so I think this was sort of one of the last concepts that we want to sort of tackle is this, you know, when you bring time into this concept of the observable universe. I mean, you can imagine that every year that goes by, the observable universe increases by 1 light year's worth of size, right?
Yes.
And so that's good news, right? More of the universe is coming into view. But the bad news is that the expansion of the universe is accelerating, and so in fact, objects at the very edges are now starting to drop off the cosmic horizon.
And so what's happening is, if you take a megaparsec to space, every second this megaparsec of space is expanding by 1 kilometer. So it's a kilometer per second per megaparsec is the way we string together all those units. But it's not just 1 kilometer. It's actually 70 kilometers plus or minus 2.2. So every megaparsec of space, every second is expanding by 70 plus or minus 2.2 kilometers. And as you look at more and more and more megaparsecs, each one of those megaparsecs is growing that same 70 plus or minus 2.2. So you have 2 megaparsecs, you've now increased every second by 140 plus or minus 4.4. That adds up. And when you get far enough away, when you get to this is one of those things we define by redshift, because everything else we have to try and observationally figure out. once something is at a redshift of 1.718, which we think currently corresponds to a light travel time, the time light has been traveling to get to us, of 9.8 billion years. Everything at that distance and further away is traveling, not traveling, it's being carried by the expansion of space at the speed of light or faster as you move further away.
Whoa, and people are going to say, hold on, Pamela, nothing can travel faster than the speed of
And
light.
it's not that they're traveling. That's why I corrected myself.
Yep.
It's not that they're traveling faster than the speed of light. It's that the space that they're sitting on is getting expanded. So they're sitting there on that moving walkway of space-time, and they're getting carried with its expansion. And that's allowed.
Yeah. And so I think as it comes back to this conversation about the observable universe, you can imagine that in the current times, the observable universe is growing. Yeah. In that there are things to observe in the observable universe. But we will reach this time in the distant future when, although the observable universe will still be increasing, of course, thanks to the speed of light, there will be nothing to see out there. And eventually it'll start to shrink. And so you will actually get this shrinking of the observable universe because the number of things that we can observe within the age of the universe has gone down.
Yeah. And one of the neat things to think about is every time we look at the cosmic microwave background, we're actually seeing something slightly different because we're seeing light that has traveled from a slightly different place. But because it was so consistent, because we're looking at cosmological distances, not human distances. We don't actually see a movie of a changing background of irregularities in the microwave background. But over, again, the fullness of time, the cosmic microwave background will be seen to change. I don't think humanity is going to last that long.
Right.
But it's just neat to think about how everything is changing, and all we're seeing is a snapshot of our universe.
Yeah, Lawrence Krauss actually came up with a really great, I don't know if it was a paper or he just had written an essay about it, sort of talking about the future of cosmology and astronomy, observational astronomy, that eventually a lot of the stuff that we now know at our current stage, age of the universe, is going to start to disappear, and that knowledge will be lost to future astronomers because all the stuff is just going to drop off the cosmic horizon.
It's only lost if we lose our documentation and we fail to spread to other worlds as our sun dies. Think of it more as it's going to become the dodo bird. It's going to become something where we have data tapes, where we have, I doubt it'll be data tapes in the future, we have recorded memory crystals that contain the Sloan Digital Sky Survey, the data from the Large Synoptic Survey Telescope, and all the information that's going to be gathered in the future. And it's like going into the Natural History Museum and seeing all of the bones of the dinosaurs. We can't see the dinosaurs, but at least we have data. And so it will still be a science.
And so, and that's a really kind of interesting thought, right? That we have a few, maybe trillion years to get our astronomy in order and to do the most detailed all-sky survey that we can possibly do before that data starts to drop off of the sky.
And it's probably not even that long. It's probably more on the order of tens of billions of years.
Right. Which kind of gets back to the fact that, just like the sun and the moon happen to appear as the same size in the sky, and so we get really cool eclipses, that we happen to live at a kind of a neat time in cosmological history where this information is available to us, that if we appeared any time later on, that it wouldn't be available to us.
And this is where there's so many good, Larry Susskind has written some excellent works on this, where it's the concept of the anthropic principle and the multiverse.
Yeah.
There's very few ways to explain the fine-tuning of our universe.
Have we done a show on the anthropic principle? I don't know if we have.
No idea.
Yeah.
Again, we've done 295.
I know. I should have these at the ready and kind of go, you listen to episode, for the anthropic principle. Yeah, no, it's great. I mean, the anthropic principle, the gist being that, we're here to observe the universe. And so, if the universe couldn't support life, and then we wouldn't be here to observe it. And so, because it does, and they're connected, which is neat. So, okay, cool. Well, thank you very much, Pamela, and we'll talk to you next week.
Sounds great, Fraser. Talk to you later. Now, don't go away. We're just saving.
Save. And yeah, you know what would be great? Using Audacity.
No. I've tried to use Audacity. I get crap when I use Audacity.
Yep. All right.
Remember, you're using either Linux or godforsaken Windows.
Windows. I am using Windows, and I apologize. It makes me sad. You have no idea.
See, at least my Mac has BSD under the hood.
Single mono channel in the exported file. Okay.
So the reason my thing died is it was trying to install a security update.
Thanks.
Yeah.
Thanks, Apple. Okay. All right. I'm safe. Hi, everybody. Okay, let's look at some questions. All right.
We got an email asking if we've heard of space cookies, and now I'm hungry.
Space cookies. IR Resources 07 on YouTube says, I cannot even imagine a four-dimensional space. And that is right, you cannot. Like your puny three-dimensional brain cannot imagine a four-dimensional space. That's sort of, we can't do that. It was funny. When we were traveling on this epic road trip that we did, we somehow got onto the topic of like multiple dimensions, and the kids were absolutely fascinated at like perspective. Like, what would it look like to a two-dimensional creature to see a cube moving through their space? And we sort of examined that and explored it, and the kids just thought that was endlessly fascinating. And they're like drawing pictures of Klein bottles and stuff. Like kids. They're so funny. Let's see. Okay,
I love
so
watching people read online.
Michael Asylum says, how do we compensate for the Earth-centric measurements we are taking?
Lots of math. We have to subtract out the Earth's motion around the sun. We have to subtract out the sun's motion around the galaxy. And we have to subtract out our galaxy's motion relative to background quasars.
So yes, we actually talked about that with the previous show with Arecibo, just like all of the math, all of the geometry that goes into this, that they do that kind of geometry with, often. And sometimes that's sort of the problem, right? When you're delivering a paper and you go up against your review committee and they kind of go, did you remember to think about this?
One of the very first announcements of a planetary discovery, they forgot to take into account the Earth's rotation.
Did they get it right, though?
No.
It wasn't a planet. So in other words, the Doppler shift they were measuring was the Earth's rotation back and forth. Oh, wah, wah. All right. Guido Bibras calls this the Melon Twister episode.
Yay!
Yay! We
More
broke people's brains. Okay, so Robert Scott Herrick asks, what's driving the expansion?
We don't. Well, so the initial, there was some cause that we cannot scientifically identify that caused that point of pure energy to cease to be a point. And then it was theorized that either there would be so much energy that it would keep expanding forever, it would eventually stop, or gravity would cause it to collapse back in on itself were the mass density high enough. Then this crazy thing called dark energy came along, and we don't know what the insert every expletive dark energy is. And it's for some reason accelerating the expansion of the universe.
Right. And what is dark energy? Don't know, but we know it's there.
Yeah.
So, and does that make people troubled?
Yes.
I love it. I love it. Seriously, we've had this conversation before, but I absolutely love the fact that there is a thing and we don't know anything about it except that it's happening. And, and people are like, well, what is dark energy? And I'm like, I don't know. And that's cool. I love that we don't know. And that's, and I wish more people would be glad to say, I don't know. What came before the Big Bang? I don't know. What's outside the universe? Well, that's a nonsense question, but also,
See,
I don't know.
I'm good with those because the answer is, I don't know.
Yes.
Science can't answer what was before the Big Bang. But with
Yes.
dark energy, the response I get is, well, get on it.
We'll get on it. Yeah, and we are. There's the dark energy probe. There's all kinds of things. So that's a great thing. It's like you just have this. You start with this faintest hint of something weird. You're like, that's weird, and then it leads you down this process of inquiry and discovery. And I think it's wonderful.
The universe gave us the worst homework problem ever.
Yeah, go figure that one out. And I just love that, and I love to say I don't know. And so when people will ask me these kinds of questions, and they're like, if you're so sure about blah blah blah, then what do you know? Where did the first life forms come from?
We're working on that.
I don't know. Like, that's okay. It's okay to say I don't know, right? You don't need to have certainty. It's nice to have uncertainty. One Ignacio says, so I have this picture of the universe, our sun inside a big square, and that square is the present time. So is there a line between the present and the past?
So the problem is, I'm looking at my hand in the past because it takes time for the light that gets reflected off of my hand to get to my eyeball. So we're always looking in the past. We never see now. Now is it's a concept. Now is what I experience inside my brain, but it's never what I observe. It's never what I see. Now, luckily, the amount of time that it takes the signal to go from my computer to my eyes is so minuscule that my brain perceives that as instantaneous. The amount of time that it takes light to go from a reporter in Saudi Arabia to a satellite back down to a television station or just back down to the television station leads to those really weird interviews where they ask a question in New York.
Yep, you hear that delay.
Measure the travel time of the light by how long it takes the other reporter to respond. That's not a bad signal. That's light travel time.
And you get that situation where the NASA scientists are trying to communicate with the Mars rover, and they send their signal. They wait an hour, they wait 20 minutes or 14 minutes, depending on how far away, or 40 minutes, and then they get their signal back. Drive forward, and then they go and have a cup of coffee, and then they come back, and the rover goes, okay, I did it, right? And that's just the time inherent. And so, everywhere you see, everything you're seeing around you is really backwards in time. You're seeing history at all times. So Michael Fields Jr. asks, and where did this point of pure energy come from? Another universe?
Science can't answer that.
Well, we don't know that science can't, because there might be, possibly, maybe, echoes of whatever was the previous structure in our current universe, right? So there could be some way, maybe, possibly, to sort of get a sense of what might, or rule out things for what might not have happened before.
Oh, okay. To reframe that, there is a certain subset of theoretical physicists who think that if the observers just get their act together, they'll be able to find echoes of the Big Bang that reveal information prior to the moment of the cosmic microwave background. This is a general theory. This is one of the sets of theories. And there is, as far as anyone is concerned, except for a few theorists out there who make their money in part by popularizing science,
who could do that? Who popularizes science?
There isn't a way to understand anything prior to the separation of the Planck length, time, distance.
And I think I hope you'll agree with me, that one of the coolest things to think about this is there's a book now by Lawrence Krauss called The Universe from Nothing, and there's also a great just talk that he did. It takes about an hour and goes through this concept and just goes into that, and doesn't necessarily speculate on what was there before, but it sort of explains why our current universe, as that it balances out to essentially zero, is quite fortunate and quite good. And I highly recommend people watch that. So it's called A Universe from Nothing. And Lawrence Krauss, was he part of this that was heard around the world?
No, he was completely fine. He was sitting on the other side of me.
Okay.
It was Neil who wasn't letting me speak, so
Right.
Neil got shushed.
Right. Right.
But Lawrence Krauss did totally school Bill Nye in that panel. So
Yeah. Yeah. Again, if anyone, there was the amazing meeting,
2 years ago.
2011.
Just Google TAM Krauss Gay Tyson
Yeah.
Nye.
Classic. Both for the content that was discussed inside of it and the hilarious interactions between Pamela and all of the blabby people on the panel. So, yeah, I highly recommend it. And Lawrence Krauss. I really like Lawrence Krauss's stuff.
Yeah.
He's great. Lee Olds says, you say that the universe is probably a four-dimensional toroidal surface. Do you have recommend any approach for getting some sort of intuitive understanding of this or getting one's head around it?
Find an artist who does sculpture.
Right, but I guess the point here is that the universe, and this is you teaching me, so I hope I get this right, that the universe is not actually a donut. It is that the way light moves in our universe, the way parallel lines work in our universe, match the way they work on a donut.
On the surface of a donut.
On the surface of a donut. And this isn't a donut, right? But it will sort of have to stand in that if you are going this way around the edge of a donut and you have two light beams, they will stay parallel. Two lines will stay parallel around the outside of the donut. And if you go this way around it, the two lines will stay parallel, and that's the behavior of the universe. But it is not actually a donut. It has the characteristics of a donut, but in four dimensions.
I can't believe you still have CDs.
No, it's Willy Wonka and the Chocolate Factory.
Okay, DVDs are left.
Yeah. Yeah. So, did I do that any justice?
Yeah, you did. You were fine.
Okay. So, but I mean, there is no way to go beyond that, right? No. Sorry.
Yeah.
Yeah. I mean, it's and this is
honestly, the only person I know who can clearly think in four dimensions is a woman I know who does sculpture for a living. And she just has magic voodoo abilities.
And she can actually think in four dimensions. So she makes four-dimensional sculptures?
She doesn't, but what she can do is a series of sculptures that represent the changing through that fourth dimension.
Right, and that's what I was mentioning, I explained to my kids, right? That you take a plane and you put your two-dimensional creatures on the plane, and then you move a sphere through the plane, and you're going to get a line that grows and then shrinks. And the two-dimensional creatures will go, well, I don't really know what that was, but I saw what it did in our universe. So we can do that, which is that we can imagine a four-dimensional object moving through our three-dimensional universe. Barely. Right?
Yes.
Who's this woman? What are these sculptures?
She does all sorts of stuff lately. She's been doing things involving arms evolving into wings. It's snail scotch. She has a variety of different things in the St. Louis area, and she's a professor at Blackburn and St. Louis University.
That's really cool. So Zucka Von Dill on YouTube asks, if the universe expands enough, does it meet itself eventually and collide?
Wrong concept. So it's not so much that it meets itself and collides as those 2 points are always in contact.
Which 2 points?
Those 2 points that we're expanding. So there is no edge to the surface. To have a collision, you have to have an edge.
Right, and so it's the same thing as you blowing up a balloon and saying, you've got if you can go around the balloon and reach your originating point and you're expanding the balloon, is there any point where the two sides of the balloon are going to collide? And no, I mean, the balloon will just grow and grow and grow.
And if you're worried about what happens in the hole of the donut, that's where I say we can't think in that many dimensions.
Michael Fields Jr. asks, the most important question I can think of, what is behind Pamela on that windowsill?
I think this is what he's asking about. It is a statue of a of a pygmy from Cameroon that to me looks like a very crazy alien. Let me hold him
It's
back
E.T.
a little
Phone
bit.
Home.
It's E.T. Phone Home, but from
Yeah.
Cameroon.
Yeah, well, that just shows that aliens that aliens have been visiting, or that Steven Spielberg got his ideas from Cameroon.
Right. So I simply found it very, very intriguing, and I kept the tag on it so I would remember where it came from. And he sits there behind me, making sure I get my job done.
Michael Asylum asks, can't you find dark energy using math and a chalkboard?
No.
No, you gotta go look for stuff. You can't just work on a chalkboard. Okay, let me see if I got any more questions here that we missed. And if anyone has any questions, we're ready. Tom Nath notes that the universe is getting fat. I guess all this talk of donuts. The Broke Astronomer says NASA's working on a warp drive, which I guess is the way that we will reach other worlds quickly.
They're going to need a lot more money to get there from here, so please support getting NASA funded. And I did not say that while wearing an employed by NASA hat.
They will need more funding, though. Vote NASA. Let's see, anything else? Dan By says, anyone's having a deja vu? Oh, that was when we were recording the episode, right? The second version. Everything is good. So if anyone's got any more questions, Ryan Consul says, so the observable universe is like the icing on the hyperdonut. That's pretty good.
Yes,
Yeah.
I'll go with that.
Right? With all the the sprinkles.
It's where one of the round sprinkles.
Yeah. Good. All right, so let me see. Oh, one more. Lance INTJ says, I was wondering if you had any recommendations for telescopes for amateur astronomers, particularly ones that would allow for decent views of deep sky objects.
Dobsonian. I like the Orion in Telescope series because they will help you find things and get started, but they don't track and they don't move for you, so it does force you to learn what you're doing.
Yeah, so if you want to see deep sky, see, you said deep sky objects. If you had just said planets, then, like maybe binoculars. A $300 binoculars or a $300, maybe like a Celestron 4-inch, yeah, or maybe a 6-inch Celestron with a nice go-to mount. You said deep sky objects, meaning you're going to want to go to a 8-inch or even a 10-inch Dobsonian. They're about $500 or $600. Yeah. And then you get really beautiful views. And I think, but then you don't get the tracking. Unless you're Corey Schmitz and you have the ability to create a amazing your own home-built tracking mount, which is, I think, really exciting to see. But yeah, and so if you want to see deep sky objects and you want a Dobsonian. If you want to take pictures of things, then it gets more expensive again. Yeah. But I don't know. I like to point people towards the tracking telescopes. I actually like,
So the problem with most tracking telescopes is to get them tracking, you have to get them perfectly aligned with the North Star.
Yeah.
And I know that has left me wanting to take hammers to telescopes.
Yeah.
And it just gets so frustrating unless you have a permanent setup. Thad Zabo, one of our colleagues who's often on the Virtual Star Party, takes these amazing images, and he must have superpowers for aligning on the North Star because he's forever camping and traveling with his telescope.
Yeah, and even when we do the Virtual Star Party, Stuart, he'll spend 15 minutes at the beginning of every episode setting up and aligning the telescope perfectly. And if he doesn't take that time, then his tracking is pretty bad, and we get very blurry images. So he needs to take that time to align it, check it, make sure it's good, take some exposures. So yeah, I mean, we get this question a lot. We always recommend go with binoculars first. When you get sick of your binoculars, then you've got sort of two directions you want to go. If you want to just observe planets and you live in a light polluted city, then get either a small Dobsonian or a really nice a tracking telescope that'll let you see the planets and the moon and stuff like that. If you do have some dark skies and you do want to go bigger, then you'll want to go with a Dobsonian if you just want to do observable. And if you want to do astrophotography, then
I actually went a middle route for astrophotography because I love my camera.
Yep.
And I also lust after a Teleview telescope I can't afford.
Yeah.
So I got one of the nice tracking mounts that Orion puts out. And we have no sponsorship from any of these people. These are honest.
Yep.
This is who we are personally buying from with no sponsorships. I bought one of the nice Orion mounts and a 300 millimeter lens. And that's if we ever get clear weather again, and I fully blame my 300 millimeter lens for the clouds. If we ever get clear weather again, that's what I'm going to be using to try and do some astrophotography.
Yeah. Tom Nath says, by the way, you can use a go-to on alt-azimuth mode and use any 3 bright stars. That's true. It is still just time-consuming and tricky, and you just need to take your time and get it done right. And so if you just want to like, oh, cool, it's a nice night sky, let's set up the telescope. Everybody come look through it. But hold on, give me 15 minutes to align it, unless you have it in a permanent mount. So that's all. That's all. I mean, it's just, you know, something to be said for just taking the big Dobsonian and swinging it into position and letting people look through the telescope. So
yeah.
Agree. Yeah. Bill Straight asks, I'm about to buy my first telescope. Can a moderately intelligent guy figure out how to find objects solo, or should I join an astronomy club? You could totally find them solo. Night Watch.
Astronomy Club makes it more fun.
Yeah, for sure. But I recommend the one that I learned with was Night Watch. I don't know about what you used, but
I used Sky and Telescope magazine.
Yeah, okay. There's a book called Night Watch by Terrence Dickinson. It's got big fold-out pages that are really great and show you all the objects, and you just start to learn the sky. And you just like, I know where Orion is, so I can find the Orion Nebula is. I know where the Pleiades is. And you could just start to find this stuff. So no, you can totally do it yourself. Just take the time. Just get out there with your telescope and just spend night after night with Night Watch or something like that and just find those objects.
Yeah.
Yeah. Cool. Okay, well, I think we're out of time. Now, we're going to record another episode in a couple of days, maybe, before the end of this week.
Hopefully, we'll see how bad Thursday gets. So the reason this is currently a little bit of chaos is this is Global Astronomy Month, and I'm working with Astronomers Without Borders to put together an Astro Art series of hangouts, and this is also grant writing season, and so they're trying to kill the astronomy community in April. April is Astronomy Month. Kill your local astronomer, apparently.
Right. Awesome. Okay, great. Well, we'll see you. Maybe there'll be another impromptu episode this week. Maybe not. We'll see what happens. If not, what's happening? Wednesday, you got your science
Learning
hour?
Space.
Yep.
Wednesday's Learning Space.
Friday, Space Hangout.
And Thursday's the Planetary Society Hangout.
Right. And then Sunday we do the virtual star party. Awesome. So much science.
So much science.
Okay. All right. We'll see you later. Thanks everyone for watching. Sorry for the mix-up. Hopefully you will now install that software on your computer and it won't cause you a problem again. The security update. All right. We'll see you later. In the various places, and I will be watching them, and if we make a mistake or if you catch something we need to fix, I will try to incorporate that into the show. So there's a bunch of places you can do that. You can make a comment or question on the event page on Google+, or if you're watching this on my feed or on Pamela's feed or somewhere on Google+, you can make a comment there, and we'll try to get all of those sources. I make no guarantees. It's a little tough to catch them all. And then probably the safest place, if you feel like no one's noticing your comments, is to make a comment over on YouTube. And so you can access the YouTube video. Just wherever you see the YouTube video, click on it and then watch it on YouTube, and you'll see separate comments that are running along YouTube, and you can post your comments in there, and it will definitely get those. So that's sort of like the safest place. And then also, if you're watching this somewhere else and you like to use Twitter, we can catch that. Just use the hashtag Astronomy Cast. And so during the show, just keep the chatter up, and we'll sort of incorporate any of those comments. And then after the show, by all means, make any comments or questions, and we'll try to stick around for a few minutes and answer your questions. I'm not sure how much time you have today, Pamela.
I have a date with my horse at 5 p.m.
Okay. Well, you're in the future. 3, so 4. So right. So we kind of want to get out of here for you around like 4. So I'm not sure how long it takes for you to get to the horse, but
I usually I leave my house to go meet my horse at 5. So we have about an hour and a half, 2 hours.
Yeah, but we're not going to stick around for an hour and a half, 2 hours.
We're
We'll probably stick around for for 15, 20 minutes after we do the show. So
I just wanted to see you convert time zones in your head.
That was an easy one because you're only 2 hours ahead of me, so that was not so bad. It's when we have to convert 3 or 4 of them all at the same time is when it gets complicated. Okay, cool. Well, let's get rolling then. I'm ready to press record. If you're ready to press record.
Yeah. Pressed record.
Testing. Yeah, that's good.
I am recording.
All right, let's do it. Here we go. Does that work?
That worked.
Okay. I think your audio is the wrong device.
Oh, really?
Tap your microphone.
Okay.
And you've spelled CosmoQuest right this time.
We all make mistakes.
That sounds way better. It was
Okay.
It was ComzoQuest last time.
Oh dear.
Oh, I forgot to mention you're the director of CosmoQuest. I'm gonna write that in my intro. Hi everybody.
Welcome to us preparing to start the audio recording of the show and inviting you in to watch backstage how everything gets done.
Yeah, exactly. Right. So, hi everyone. My name's Fraser. I'm the publisher of Universe Today, and there's Dr. Pamela Gay, my co-host on Astronomy Cast, and this is an impromptu catch-up episode of Astronomy Cast. So, as you may know, we're a few episodes behind, just a couple, not many, and so we are absolutely committed to catching these up as quickly as humanly possible. And so, we're going to be doing a few more of these impromptu episodes, and catching them up to the feed, because I know the feed is a little behind as well. So, so thank you everybody who has noticed this is a problem. It is a daily reminder that we are behind, and we will get caught up. So anyway, so today we're going to do a live episode of Astronomy Cast. We're going to record that. It'll take us about half an hour, and today's episode we're going to be talking about the observable and unobservable universe. And so that'll take us about half an hour, and feel free to make any comment, questions, posts while we're doing the show. Sylvan Westby wants to remind you, are you recording in stereo?
No, I'm
Okay.
not.
Right.
Valid question.
Valid question. Very valid. So right, and so you can, by all means, make any comments or questions in Astronomy Cast, episode 295 for Monday, February 25th, 2013, The Observable Universe. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. Do we have any announcements or things to talk about?
We do. We
Okay.
are continuing to advertise for the classes that are going to be starting soon through CosmoQuest. You can get to them by going to CosmoQuest/classes.
CosmoQuest.org/classes?
Yeah, cosmoquest.org/classes. And we currently have 2 upcoming classes. One of them is on the sun, stars, and stellar evolution. That one is taught by Rain Sanders, who goes by Dear Astronomer on Twitter. The other class is cosmology, taught by Dr. M.R. Francis Matthew. He shows up as Dr. Mr. Francis on Twitter, which amuses me to no end.
Yeah.
He is teaching a class on cosmology. Both of these classes are starting shortly in April, so you can go to cosmoquest.org/classes, check out the dates, check out the times, and hopefully you'll sign up through Eventbrite. Nicole Gallucci and I will both be making random appearances in these classes and contributing where we can. And this is one of those ways that we help employ people who are in astronomy, so we do ask you to please pay. This is part of how these 2 individuals make their living. Sorry that we can't do everything for free. I know we would if we could, but we're hoping that you'll sign up. Each is 8 hours long and jam-packed with information. And the classes are limited to 8 people each.
Perfect. All right, let's get on with the actual show part here. So we understand that our place in the universe because of the direct observation. So we can see the light that traveled billions of light years across space to reach us. This sphere of space is the observable universe, everything we can detect. But it's really just a fraction of the larger unobservable universe. And today we'll talk about both.